recording, and I will turn things over to Ron.
Well, thank you, Norval. Thank you for that kind introduction, and I'm pleased to welcome you all today to today's webinar on quality by design. Speaking to you from Delaware, and it's a snowy day here in Delaware, so it looks like we're going to get a little bit of the white stuff. First, a little bit of context and background on quality by design. You might be thinking about it as it's most useful in the design of products and processes, and it is useful there, but it's also useful in manufacturing and in technology transfer. So it's a very broad approach, and we're going to show you how broad and holistic it really is. It's a proven methodology. It started in the 1950s or so. I would say that the reason it's works so well is it's the right thing to do. I was introduced to the subject in graduate school, and I worked at DuPont for 24 years and used the methodology there. So it's been around a while, and we've learned a lot. So while it's been around a while, we'll keep learning, and we're making it better. And what I'm going to show you today is how we can integrate it into a holistic approach and also a risk-based approach. So let's see. If I could only get this doggone slide to move forward.
Looks like you may need to turn the marker off.
Let's do that. I did that, Norval. That doesn't seem to help us here.
Okay, interesting. Can you turn the eraser off? I see the eraser.
How about page down on the keyboard?
Yours, that's fine.
I've tried page down on the keyboard. I've tried enter, arrows. I've tried just about everything I know how.
Okay. Try going out of slideshow mode and then coming back into it. Hey, there you go.
Okay, so our agenda for today, we're going to talk a little bit about the what and the why of QBD. We're going to talk about the building blocks of quality by design. A lot of people get confused because there's different aspects to it. Hopefully these building blocks will help straighten some of that out. We'll talk about defining what is known in some worlds as the design space, in other words as the operating window. We'll talk about assessing risk and its relationship to variation, predicting process performance, and I'll share with you a quality by design framework for monitoring and improving production. I would like to think that this is almost a seminal framework. It's something that you don't see elsewhere, and then of course there'll be summary, and I welcome your comments at the end and questions, and I'd like to help you out in any way I can. QBD, like I mentioned, goes back into the 1950s, but it was popularized in the 1980s whenever there was the NBC white paper, "If Japan can do it, why can't we?" And if you haven't seen that, you can find it on YouTube. It's really important. It's an important thing in the whole quality revolution. AT&T picked up on quality by design in a big way, and they published an article in 1986 in Quality Progress. Quality by design has been re-energized by the pharmaceutical industry beginning in the early 2000s, following the lead of the Food and Drug Administration. And if you're not familiar with what's been going on in the pharmaceutical industry, I encourage you to check that out, because they're really doing some leading-edge work that's really applicable in any industry. More recently, risk reduction and risk management has become a keen and important focus, and that's all integral to the quality by design thinking. So it's an opportunity for us to revisit quality by design and deepen our understanding of the quality by design building blocks. The basis for what you're going to hear me say today, I published an article in Quality Progress in May of 2016, which actually I'm happy to share it with you, but if for whatever reason you can't get it. Here's the front page of that article, and it's such a neat picture, I just thought I'd share it with you. That's Quality Progress does a nice job with introducing their articles. So quality by design, it's an effective approach. It's about building quality into products and processes in both design and the manufacturing stages. It's been defined by a number of people, but this is the definition that seems to be most popular and, in my view, the most useful. It's a strategic approach to quality and process development, to product and process development, beginning with pre-design objectives, defined objectives, emphasizing product and process understanding and process control based on sound science and quality risk management. Those key words that I've highlighted there, those are important, and we need to understand those. But key to this, and if any of you taking any notes, write down the word systematic, because that's really important, is that we have a systematic approach which quality by design delivers. Here are the building blocks of quality by design. First, it's the identification of the critical to quality attributes of the product. It's about raw material variation and characterization, and characterizing the variation. A lot of people don't pay enough attention to raw material variation. It's about identifying critical process parameters, which we call CPPs. It's a characterization of the design space or operating window where we're going to operate the process. It's about process capability, control, and robustness. And it's also about analytical method or test method capability, control, and robustness. In my experience, organizations don't pay enough attention to test method development and maintenance, and so it's really important that we do so. It's about risk analysis and risk management, which are really becoming into vogue these days. People recognize the importance of doing risk analysis, and that's integral to quality by design. And it's about life cycle management of the system, all the way from developing the product to the very end, whenever the product is no longer used. So it's ongoing checking and enhancement and continued process, what we call continued process verification, and I'll show you a methodology for doing that. Along the way, when we do all of this, we put together these building blocks, and we understand them. We end up really understanding the process. And if you remember, that's one of the key things that was integral to the definition of quality by design. So let's see how these building blocks fit together. It's one thing to see them in a list. It's something else to see how they fit together. So we're going to start over here on the right-hand side where the risk level, and you see it's got a bunch of arrows coming into it. Those are the inputs to the risk level. The design space, or the operating, where we operate the process, is a critical input, as well as process control. We're now going to move over to the left-hand side of the slide where we have the critical quality attributes, the critical process parameters, and raw material variation. And then we're in a position to assess process capability and then develop what we call the process model, which engineers and others like to represent as y is a function of x. So the y's here, if you look, the critical, on the left-hand side, you see the critical quality attributes. Critical process parameters are the x's. In this model, and we'll talk some more about this, this is where the process understanding actually resides, in that process model. We also need to worry about something called process robustness, and we'll talk some more about that. And finally, how the process can fail, doing a failure modes and effect analysis. So those are the key building blocks of quality by design. At the bottom, you'll notice that I've said that process in this particular figure is the operational or manufacturing process plus the analytical or test method process. And I've combined that all into a single process here just to make the slide less complicated. Now, the important thing is you'll notice here that all of these building blocks, they're linked together and they're sequenced. So it's important to recognize the linkage and the sequence. And so for you, those of you who already have processes and have manufacturing processes operating, these are kind of the key elements that you need to pay attention to in order to have a very effective and useful manufacturing process. Now also, this quality by the building blocks is not a one-time event. It's something that you put together your process, you launch it, and you continue through it. And so continue through the life of the process. So we have to pay attention to life cycle management and continuous improvement. And what some people call continued process verification, which also comes under the name of process control, but continued process verification is more than process control, as you'll see here in a little bit. Now let's talk about the design space or the operating window. It's a fundamental element of quality by design, and here we define it as it's the multidimensional combination and interaction of input variables and process variables that have been demonstrated to provide assurance of quality. So if you look at the Venn diagram down in the left-hand corner, you see the red area is the knowledge space. The design space is where is that combination of variables, in the knowledge space where we can effectively operate the process. But obviously we have to control it. We need to have a process target. And there's a couple different, here we're showing that we can have a couple different targets depending on the product produced or what have you, and we're calling those control spaces Q and Z. The key thing to creating the design space or operating window is process understanding. We mentioned that earlier, and so we need to develop process understanding. And believe it or not, there's a lot of processes in our world today that produce products which are used, but we really don't understand those processes. And if you don't understand a process, it's very difficult to improve it or make it more effective. So we're after process understanding. Here we're going to continue with our discussion of the design space. And the example that I have here is a pharmaceutical tablet. Those of you who take pharmaceutical tablets for whatever ailments and so forth. A key characteristic of a pharmaceutical tablet is dissolution, how fast the tablet dissolves and gets into your system. And so in this particular example, we're saying that our specification is that dissolution needs to be greater than 80% in a certain time period. And you'll notice that we have what we call a contour plot of dissolution as a function of two process parameters, labeled parameters 1 and 2. Now, as with all products, there's more than one characteristic that defines it, and also for a pharmaceutical tablet, another key variable is friability. And in this case, the specification is less than 2%. And so the white area is the combination of parameters 1 and 2, process parameters 1 and 2 that will have friability less than 2%. Well, of course, what you'd like to have in your product definitions, you'd like your dissolution greater than 80% and friability less than 2%. When you overlay those two contour plots, you get something which looks like this, and the white area in the middle is what we call the design space or the region of operability. So those are the combinations of parameters 1 and process parameters 1 and 2 that will meet the specifications of dissolution greater than 80%, friability specification less than 2%. Here's another example of a product that I worked on for one of my clients. This happens to be, again, a pharmaceutical tablet. And there's two different variables here, the two process parameters. One on the x-axis is the drug particle size. The other one is the excipient concentration. And here again, the critical parameter, if you look on the right-hand side, is dissolution, where it has a 10-minute specification, a 15-minute specification, a 30-minute specification, and a 45-minute specification. The white area is the combination of drug particle size and excipient concentration that will meet all of those specifications. So we can manufacture the product. The design space is all of the white area, and typically we're going to pick a process target. In this particular case, we're showing something close to the center of the design space. Now we have a critical question here is, how do we keep this process on target? We have a target of 90 at 11.5. We're going to need a process control system to keep it on target. So that's another critical building block, as you saw earlier, for quality by design. This is kind of interesting, at least I find it interesting, on how the design space concept in the pharmaceutical world anyway evolved. It started out in the 1920s when Sir Ronald Fisher invented the whole field of design of experiments. Fast forward into the 1950s, and George Box creates what is known as response surface methodology, working for Imperial Chemicals Industries in Britain. And he creates response surface methodology, which helps us define what the operating window might be. Moving into the 70s, Joe Schwartz was working for the pharmaceutical company Merck. He later moved on to the University of Sciences in Philadelphia, where he introduced the whole idea of response surface methodology and the operating window into the pharmaceutical industry in the late 60s and early 70s. In the early 2000s, A.J.S. Hussain at the FDA began providing leadership in how we're going to use what was called quality by design in the design space in the pharmaceutical industry. And so he talked with Schwartz, learned what he could from Schwartz, and then began promoting it in the pharmaceutical industry. So you see, something started in the 1920s in one industry. Well, I guess we could say it this way: 20s into the 50s and early 60s, why the chemical and process industries knew about it, but it took a while into the 2000s before it found its way into the pharmaceutical industry. So that path I find interesting. Perhaps you'll find some interest as well, and it's described in greater detail in the reference that you see at the bottom. A key thing when we talk about quality by design is that we need to recognize that it's about variation. And Deming, the quality guru, said it really, I think, very well. He said, if I had to reduce my message for management to just a few words, I'd say that it all had to do about reducing variation. So let's explore that for a little bit. And variation is also related to process understanding and risk reduction. So we'll start over here on the right-hand side, where we want to end up with enhanced compliance and reduced risk. And we move to the left-hand side. One of the key drivers is process variation. We analyze that variation. That produces process understanding. That process understanding, we can now reduce process variation. We can enhance our prediction of process performance, and as a result, we get enhanced compliance and reduced risk. Another way of looking at this, and this is really important because a lot of people don't seem to recognize this, is that there's a direct relationship between variation and risk. As variation increases, risk also increases. And variation is also related to quality. Deming taught us this: as variation increases, quality decreases. We know that costs go up as variation increases, and customer satisfaction goes down as variation increases. So you can see that variation is a key driver of the things that we worry about a lot: risk, quality, cost, customer satisfaction. So our objective, what we want is we want low variation. That low variation is going to give us low risk. It's going to give us high quality. It's going to give us low cost, and it's going to give us high customer satisfaction. So the whole idea of understanding, the bottom line, understanding and reducing variation is a good thing. So it all starts with understanding variation. As I mentioned earlier, you can't control, improve, or transfer a process that you don't understand. So as variation increases, your process understanding decreases. So that's a good thing to keep in mind whenever you see a process that is highly variable, producing product which can't meet specifications and so forth. There's a very good chance that nobody really understands how to understands how that process operates. Now, let's move to the next important piece of quality by design, and that is predicting process performance. And here's a generic manufacturing process. We have inputs to this process, which we call X's: raw materials, water, energy. The outputs of the process are things like yield and waste and capacity, downtime, production rate. We have some knobs on the process that we can control the process, things like temperatures and pressures, flow rate, catalyst concentration. And then we have some uncontrolled variables that affect the process, which are also X's, things like ambient conditions, temperatures and humidities, shift, team, operators, machine, raw material lot. We mentioned that earlier. One of the key components, key building blocks of quality by design, understanding the characterizing the variation in raw material. These are important variables that we don't have a lot of control over, but yet they affect the output. And so now we have our model, y is a function of x, which enables us to predict future performance for the process. And that equation, y is a function of x, you can look at it as a what can I say, a schematic of a process, but what we're really talking about is when we say y is a function of x, we're talking about quantitative models, equations. Here's an example. This is a roller compaction study where they're producing tablets, pharmaceutical tablets. The model, you can see the tablet potency is 98 plus 6/10 of roller force. Roller force is a part of the process that's producing the tablet. So we have an equation, very simple equation, that the y, tablet potency, is a function of just 1x, roller force. But for that same process, we have another important variable, content uniformity. We want the content of the tablets to be uniform so that everybody gets the right dose. And now you can see an equation here where the uniformity, or relative standard deviation, is a negative function of roller force, a positive function of mill screen, and a negative function of gap width. So if you read the reference that I have there, you'll see it talked about it more. So the important thing is we're going to build models where we're going to relate the output of the process as a function of the inputs, and those models are going to help us better understand the process as well as telling us where we ought to operate the process in the form of the operating window or the design space. Now, let me back up a minute here. No, this isn't what I wanted. Hang on, I'll get there. get to the process schematic. Now, whenever you look at here's our process schematic. When you look at this, you can see that we have got on the Y side, there's 5 output variables. And then if you look at the X's, there's 1, 2, 3, 4, 5, 6, 7, about another 13 or 14. So we got a large number of potential important variables. And actually, when you create this is just a high-level schematic. But whenever you generate these kinds of schematics, we often see 30 or 40 potential variables. And so you're probably thinking, or maybe thinking, well, gee, how do we get, how do we deal with such a large number of variables? And you'll notice these equations that I just showed you are rather small, just a function of a few variables. Well, the thing that we have working for us is something called the Pareto Principle. The Pareto Principle says that 80% of the variation in the output, or Y, is due to 20% of the causes, which is the X's. And actually, in experience, that 80% translates into about 3 to 6 key variables. So while you may have 30 or 40 candidate variables, there's typically only 3 to 6 that really drive the process. And so what you need is an approach that can funnel those large number of variables down to some smaller number. And of course, following the quality by design approach gets you to that position. And if you don't get there, here's a story of something that a real story shows you what can happen. This is a major product. It happens to be a pharmaceutical product again. It's in late stage development. They've been working on it for 8 years, and they haven't been able to get it validated to the point that they can get it approved by the FDA and begin to manufacture it. And it is what we would call a blockbuster drug. Very important drug, huge market, lots of money involved. Well, they went and took a QPD approach to this. Some of my colleagues did this work. And one of the tools they used was design of experiments. And what they did is they looked at 9 variables, 5 process variables, and 4 raw material variables. And they learned 2 very important things. First thing they learned is that there were interactions between the raw material variables and the process variables. This often happens, and I've seen it happen in many different processes. And so if you don't study those variables, raw material variables and process variables simultaneously, you can get yourself into all kinds of problems, which this organization did. The other important study that came out of this designed experiment was that the variable that had the largest effect, the importance of that variable, was unknown until they ran this experiment. So they have been studying this process for 8 years, and they hadn't identified what the most important variable was, and of course that's the reason they couldn't get it validated. Well, they had to tighten up a few specifications on raw materials, and whenever they were able to get all that done, took them about a year. They had the product on the market in a year. So what they couldn't get done in 8 years, it took them a year to get done. Now, this isn't to say that they hadn't learned anything over the 8 years, but they sure hadn't gotten it through validation. And the reason, in my view, is that they just hadn't taken a very good strategic look and tried to make sure that they looked at all the variables, took a holistic approach, and tried to find out how can we look at all the variables at once and then narrow our focus down to that 6 or 8 key variables. So that's a case where quality by design helped them get the product on the market. Another piece here is that quality by design can provide a very effective production monitoring system. And so here's what that system will look like. If we've got a batch production, producing material over time. We get data on the product, batch quality data, and there's a periodic analysis and review of that data. And out of that periodic analysis and review, Maybe there's some process adjustments we need to make in order to get the process back on target. Well, the process models, this y as a function of x, tells us what variables, how we can change the different variables to get the process back on target. And of course, this analysis goes on. I guess I ought to talk over here some of the monitoring tools that are used in doing this analysis and review. There's things like control charts, capability analysis, process variance components, histograms, Pareto charts, and other kinds of things. But as we do this analysis for processes, from time to time, we find out that, lo and behold, try as we might, we just can't. The need for process adjustments continues to arise. So what that says is, over on the right-hand side now, we need to move into a process improvement phase using the DMAIC model, DMAIC. We'll talk about that in a moment. So they do the process improvements, which lead to improvements to the batch production. Now, so this is a high-level schematic. There's lots to go along with it, but that gets out right in front of you on one page what a framework for production monitoring system might look like, and utilize quality by design thinking. So here are some other quality by design tools that reduce risk. These are important aspects here. And we've mentioned them. I've kind of summarized them here. Design of experiments, making sure you identify the critical variables. Process control, creating and maintaining stable and capable processes. Test methods that perform well with minimum variance. We want them to be robust and produce quality data. Robustness of products and processes, and then failure modes and effect analysis. And basically, this is a way of learning how can the process fail, and then, of course, what you want to do is mitigate those problems so that they either don't occur or certainly don't reoccur. Now, I won't say a whole lot about this, but I did mention earlier the importance of looking at test method development. And so this slide summarizes the various types of studies that are done in order to create and improve test methods. Things like design of experiments plays a role, gauge R&R studies, test method robustness. I just meant something about using blind controls to assess the stability of your process. And process variation studies, looking at not only manufacturing variation, but also sampling and test variation, and of course, interlaboratory studies. Now, you can also use quality by design to reduce costs. We live in a cost containment environment. Costs are very, very important. And what we want to do is identify problems and issues that have the greatest cost impact. And QBD can help us deal with these issues. Here's just a couple of examples that shows how opportunities were found in manufacturing, which led to significant bottom line results. The first one here is a mixing operation, and its performance was really poor. And so they did a quality by design study, and lo and behold, they found it was really had to do with the blades on the mixers had some issues with them, and they were able to improve the performance by 4.1%, which led to about a $750,000 per year cost savings. Another one here is improved coder reliability, reduced product losses, saving about $1.7 million. This was really an interesting one because what the problem was is that whenever the process would run into problems, either maintenance problems or faulty operational problems, they had a very poor procedure for getting spare parts to the process, which resulted in a lot of downtime, product losses, and so forth. So it wasn't the process that was the problem, it was how we're going to maintain the process and have equipment, parts and spare parts, and so forth. So this is just an example here, too, of, again, in both of these, increased process understanding leading to improved quality and reduced cost. So to summarize, and then we'll have some time for questions, I see, QBD is an effective approach, certainly for producing new products and processes, but also for optimization and improvement of existing processes. And enabling effective technology transfer. We need to keep in mind that even though you have a good process, we live in a dynamic world, Murphy's Law and everything, and that things get, if left alone, get poorer over time. And so that we need to continually work on optimization and improvement of existing processes. And the whole thought process and this holistic model of quality by design that I've shown you can help you in that regard. I've emphasized the importance of process understanding. It's fundamental to creating the design space and sustaining performance. So the design space where we're going to operate the process, and then sustaining performance over time, make sure that we stay on that process target. Results, certainly faster developments of products and processes. You get to market faster. I showed you an example of where they had worked for 8 years and they couldn't get the product on the market. And using quality by design over a year's period of time, they were successful. Help you keep process performance on target within specification at minimum cost with less waste. And all of that helps improve customer satisfaction and leads to bottom line results. So it's been effective for over 40 years. It's getting better and better as we learn how to use it. And so I encourage you to think about it and see how ways you can use this a holistic approach in how you design and operate your processes and organizations. There's some references which summarize a lot of the stuff that I've mentioned. So we'll leave that. There's some one of the key tools of quality by design, of course, is design of experiments. Here's some references on design of experiments. So at that point, I'm going to stop and see if we have any questions or things that we want to talk about. I'll leave my message up to remind you about that a little bit. And Norval, have you gotten any questions on your chat line?
Thanks, Ron. Yes, we do have one question at this point. Somebody wanted me to ask you if you are going to the World Conference in Seattle at the end of next month.
Yes, I will be there.
Oh, great. Okay. Good.
I will.
Will you be a speaker there?
I will not be a speaker. I guess I'll brag a little bit on myself. I will be inducted as an honorary member of ASQ at that meeting. But I'll be around. I'll be happy to talk with people. You've got my contact information. If you want to talk with me there, be happy to do that.
Well, congratulations on your honorary membership.
Thank you.
Folks, if you have questions for Ron, please go ahead and type them into the chat box. We have 121 people online, not including folks who just called in by phone or who did not log in to the WebEx. So that's a terrific turnout today. Thank you very much. Questions coming in, Ron. The first one, regarding correlation versus causation. If a variable fits into an equation, does that mean it's no longer superstition?
Well, you've moved down the road to it's no longer superstition, but with all of these models, I mean, these are empirical models. What you need to do is you need to validate those models with what we call confirmation experiments or confirmation studies to demonstrate that, in fact, you can measure what these models are predicting. So, thou shalt confirm is the admonition.
Okay. Somebody did ask the question if the slide deck will be distributed. I can answer that one. Ron has already shared the slide deck with me, and we do have his permission to share that with everybody who is online. So that will be included in the follow-up here later this afternoon. So be expecting that. The next question for Ron is, what automated tools can you recommend for QBD?
Well, certainly, in order to do QBD, you need to have availability to you some good statistical software. There's several good software packages, statistical software packages on the market. One of them goes by the name of JUMP, J-M-P. It's a SaaS product. Another one is Minitab. There's one out there also, Statistica. On the product design part, there's something called Design Ease. So I think you need to get yourself a good statistical package. Another thing I think you need to move forward with is getting some good database management. We're getting our systems are using more and more data. And so we need a way to access that data, and then, of course, we can use the statistical software to do the analysis. So those are some thoughts on software.
Okay. We're going to move on to the next question. The next question for Ron, where is Lean's place in QBD?
Well, some of the processes that are involved in your manufacturing that are what can I say, are time-based. Let's think of it this way. I'll give you an example. One is batch release. That you can't release a product until the batch records have been reviewed. And I worked on a project where it took a very long time for people to review the batch records, and of course you couldn't release the product until the batch records had been approved. And using Lean, so that the critical metric there is cycle time. And so looking at cycle time and using actually a combination of Lean methods and Six Sigma methods, able to cut those batch review times, or batch record review times, I should say, in as much as a half or 30%, saving millions of dollars. So it's Lean is another process improvement tool. Maybe that's another way to think about it.
Okay. Let's see. We don't have any other questions showing up. Ron, if you go out of slideshow mode on your side, you may have had some oh, wait a minute. No, we got more coming in. Okay. QBD looks a great deal like ISO 9001 plus IATF 16949 plus ISO 17025, which we have to adhere to as a supplier to the automotive industry. Any comments?
Well, I've not personally observed the comment, but not surprised, because you've got different standards out there, and sometimes the standards don't look as broad as they could. And so what that would suggest is you collect those different standards together, and those bases are covered by quality by design.
Okay, the next question we have, can we see the slide with the inputs, outputs, controlled variables, and uncontrolled variables again? There is a question regarding how the X values are determined.
Well, the X values are simply measurements. Like, I'm not sure what, in all of these, well, not all of these, but a lot of these, I mean, you're going to measure, you want the X values. Well, temperature, would be the temperature that the process operates. Pressure, the pressure that the process operates. A flow rate is how fast material is flowing through the process. Catalyst concentration would be an ingredient. What concentration do you have? Raw materials, typically what they'd be raw material quality characteristics. Water and energy would be amounts. You get down here to the uncontrolled variables. This is tougher. It's tougher to get, what's the ambient temperature, ambient humidity, but those can be measured. Shift is basically which shift is it on? Is it a 3-shift operation or a 2-shift operation? Different teams, some processes will have different teams, so that would be like teams A, B, C, and D, or A, B, and C, depending on whether it's a 3-team or a 4-team operation. Operators, different machines, and so forth. So they're typically quantitative measurements or qualitative characteristics or quantitative measurements to determine the X's.
Okay, we do have a comment. I think the new IATF 16949 was heading this direction in terms of focusing more on continuous improvement in the design process as opposed to just improving existing processes.
Well, that's good to know.
Okay, I didn't know maybe if you had anything additional to add to that. I wasn't sure.
Yeah, no, unfortunately I don't. Unfortunately.
Okay. Oh, the comment just came in, just building off the previous question. Okay, so that was a shared statement. Okay. Let's see. Does anybody else have any other questions for Ron? We do have a few more minutes here before the top of the hour.
Well, one
Ron,
other thing.
Oh, I'm just going to say, if you click on chat, now that you're out of slide screen or slideshow mode, if you click on chat, you should be able to see the chat box. There may be some questions that came directly to you that I am not able to see.
I'm not going to be able to, I don't think I'm going to be able to get there. But there is one important question which hasn't come up yet.
Okay.
Is what does it cost to do QBD? Well, as with anything, there's a learning curve. But the learning curve is not that steep. We do have the software that helps us quite a bit. My experience is quality by design projects typically return anywhere from a 4-to-1 to a 10-to-1 ratio. You get $10 back for every dollar you spend on the implementation of QBD, or anywhere from 4-to-1 to 10-to-1. So it is a cost-effective approach, and it's also a gift that keeps on giving. Once you improve processes or design them better, you get that return this year, but you're going to get that same return next year and the year after that. So there's it's a very effective way to do business.
Okay, in the meantime, we had another comment that came across that said that someone else would agree with the IATF 16949 comment. There's a lot more emphasis on design.
Well, that's a good thing in the sense that, if the processes aren't designed well, they're not going to perform well. So having greater emphasis on design and getting the design right pays dividends down the road for years to come.
Okay.
And Norval, give me that number again for that standard.
The last one I said?
Yeah.
IATF 16949. It was previously TS 16949, but it was recently changed to IATF 16949.
Okay, good. Thank you.
It looks like we don't have any other questions coming through. Oh, yes, we do. Just when we thought we didn't. Do you have any suggestions for good risk management tools?
Well, a couple of things. Certainly, failure modes and effect analysis is very effective in identifying risks and figuring out how to mitigate them. So that is a very effective tool. The other point that I would make is that a lot of the tools that we commonly use, statistically based tools, are based on risk and risk reduction. Like if you go back and you look at the material, I said something about design of experiments. It's going to reduce the risk of missing an important variable. If you do capability statistics, capability statistics can help calculate the probability that you're going to have defective product. Gauge R&R studies reduce the risk of having measurements which are going to be highly variable, which again increase risk. So a lot of the tools, my message is, you have to think about this a little bit, a lot of the tools that we have been routinely using in dealing with the analysis and improvement and design of processes have risk built right into them. So these are really effective risk reduction tools. They just haven't been recognized as such.
Okay, it looks like we don't have any further questions. With that in mind, one last moment here. Reminder that our next webinar will be scheduled 2 weeks from today. It'll be on Tuesday, April 3rd. It'll be John Lafferty presenting on how DMAIC helped improve a village in West Africa. We do have a lot of folks who are registered for that. We still have plenty of space available. If you're interested in registering for that, plenty of time for that as well. We will be taking a break next week. We will not be online next week with the spring break and holiday coming up, right around the corner here in April. We're going to take a break. We'll be back online Tuesday, April 3rd. Anyway, I'd like to take a moment just to thank Ron for presenting for us today. Thank you, Ron.
Thank you. Pleased to be part of this.
Yeah, and glad to have you. And we'll also like to thank everyone who tuned in today. We hope that everybody has a great rest of the day, and we will hopefully see you online again soon. Until Tuesday, April 3rd, thanks everyone, and we'll see you soon. Bye now.
Bye-bye.